Hi, my name's Lorenzo. I work at Oracle on the kernel team with a focus on upstream, and I also co-maintain memory mapping, transparent huge pages, and the reverse mapping in the memory management subsystem. So I think a really interesting thought experiment often is to take a really simple question and just go all the way through with it and see what you discover. And this is what this talk is. We're simply asking, where does my memory come from? So a kind of top-down view might be something like this, where we have an application. It does an allocation in the form of something like malloc, goes to the system library, perhaps glibc, some kind of internal implementation details, and then when it needs memory from the kernel, invokes either the break system call, the mmap system call. But of course, this is not quite what's happening. When you do this, nothing is allocated at all. In fact, all we do is update kernel metadata. So every process has a mmstruct data structure associated with it, and within that there's a maple tree, which is a kind of enhanced B tree, a data structure which underneath it contains ranges of these things called VMAs, or virtual memory areas, and they describe valid userland mappings for that process with equal attributes, or the attributes in that range are all the same. So when you're doing an mmap, you're essentially asking to set up a VMA. And how would you do that? I mean, this is an example of how you might do that. Just a very simple mmap call. You're giving the size, you don't care about the address, give some attributes, and then you get back a pointer, which you are then going to work with. But that pointer is actually simply designating the start of the VMA. Although that's not quite true either, because if you happen to map memory this way, and it's immediately adjacent to another VMA, we'll merge it. So you may get a pointer that is actually midway through a VMA, but of course it's still valid memory at the size that you requested. So kind of the theme of this talk is things are not often quite as they seem, and we'll dig deeper. There's also break, which fundamentally does something similar. That you have all of this data that is associated with the program loaded into memory, and above that you have the heap, an area designated as a heap, and the address at the top of that, the largest address is called the program break, and if you request the kernel to increase that, then you get more memory mapped, and if you shrink it, you free that up. And that's essentially just expanding or contracting a VMA in practice. So take two of where my memory comes from. Now we know a little bit more. Application, malloc, glibc, some kind of internal implementation details, break or mmap, and then we get a VMA. Well, of course, that's not it, because how do you get your memory? That doesn't really give you the information you need at all. So we're going to dwell on this side a little bit, because it's very important. So if you have sane hardware, the memory that you work with is virtual. So there's a distinction between virtual and physical addresses when it comes to memory. The physical address essentially tells the CPU where to look. It's on this DDR DIMM in this slot, and it's at this cell, or this row, this offset. It will all be encoded in the physical address, but we can't just let programs play with these addresses like that, because then they will trample all over each other, and there will be no distinction between the processes, and it really limits your ability to control everything. So instead, we essentially say we can have, not quite true, but we can have kind of arbitrary virtual addresses that we then map onto physical addresses, and each process has its own set. And in order to do that, we need to have a way of mapping between the two that's sensible. So if we simply had a table that listed every virtual address and every physical address, that couldn't possibly work, because it would end up taking up all of physical memory to try and map memory, and that's not very practical. So instead, we have a sparse mapping between the two. And one thing to note here is you can't operate at the byte granularity. That is too fine-grained. To be practical, we've got to operate at a certain level of granularity we call the base page size, which typically, although nowadays it's often different, but typically 4 kilobytes. So we'll just talk about a 4 kilobyte situation here. And in order to perform the sparse mapping, we use this these structures called page tables, and each of them essentially provide a gradually narrowing range in which they describe. So the aim is to use the absolute minimal amount of memory to map between virtual and physical. So you start off with the first topmost level of page table, the global directory, the PGD, and every entry in there, which by the way is the size of a page, so it's the minimum size you can work with. Right? So there's 512 entries for a 64-bit system, and each entry spans 512 gigabytes. And each of those entries will contain a physical address for the next level in the hierarchy, which narrows further. So then you have the next level, PUD, that spans 1 gigabyte for each entry, and then PMD, which is 2 megabytes, and finally PTE, which gives you the physical address of the actual data. And it's kind of neatly encoded. The virtual address, the least significant 12 bits, give you the offset into the data page, and every block of 9 bits above gives you the index into each of the page tables. And because everything has to be aligned, i.e. to 4 kilobytes, i.e. the lower 12 bits of the physical address have to be 0, this is something actually the hardware is aware of, so it ignores those bits for the purposes of the address, but you can put information in there, such as whether the entries are read-write, and so on. So this already gives us a great deal of power, and it allows us to use a minimal amount of memory for mappings that are mostly going to be empty. So if they're empty, we try very hard not to use any memory for that. So that gives you actually, in practice, about 128 terabytes of memory that you could map, although modern systems, you go up to 64 petabytes in theory. So this is how the page tables are set up, but we've not spoken about how you get the memory. So we've only set up the metadata. That's all we've done so far with the mmap call. So what happens actually when you try and use that pointer, CPU raises a fault because it has no idea what the page tables are, and luckily, very luckily, it hooks into the kernel. You can have the kernel hook into that, and then the kernel can go and do whatever it needs to do, and then it will context switch back to userland, and it will try the operation again. So that allows us, for valid memory ranges, to do what we call faulting in the page table, so allocating any page tables we need, and the final data page. So this is where that happens, and this is where the valid ranges really matter, because here you can see if it's not valid, then you can segfault the process, right? So this is a very powerful thing. It's called demand paging, and it's kind of the basis of how modern memory management works. So another aspect here as well is we've spoken about how we get this virtual mapping into place, but what about the physical allocation of the memory, actually getting these we've got this set of physical memory we need to dish out, and how do we do that? So we use a very modern algorithm from 1963 by Harry Markowitz. This happens a lot in computer science, where you can trace things back to the 50s and 60s. Described very well in The Art of Computer Programming by Donald Knuth. So yeah, this is called a buddy allocator, is the algorithm we use. And one thing to note here is that we often need to have blocks of memory that have contiguous physical memory that's larger than one base page in size. For instance, transparent huge pages requires that, and also there are other situations where you require it as well. So the allocator needs to handle that. And so the way it works is you, kind of broadly speaking, at the beginning of time, or the time at which the buddy allocator is set up, we divide memory into the maximum order size, and then we have free lists for every order size. And an order, just to clarify, is we're using the magical power of the power of 2 here. So every page that's dished out by this will be the power of 2 number of base pages, and the order is that power. So order 0 is 2 to the power 0, so 1 page. Order 1 is 2 to the power 1, so 2 pages, and so on and so on. So coming back to how we initialize this, we'll essentially have a free list that everything is at the maximum order size. And then if you wanted to, say, allocate an order 0 page from that, we have this process where we can just, because it's all power of 2, we can just keep dividing by 2 until we get the order we need. And this is what this diagram is showing. And each time we divide by 2, we get 2 pages of the next lowest order, and one of those we can put on the free list for that order. And we go all the way down until we get the page we need. But the real power here is that when you free that memory, Each time that you divide into two, the other part is very easy to determine numerically mathematically what that address of that is. And so that's termed the page's buddy, hence buddy allocator. And so that means when you free, let's say we just allocated that page and it freed it immediately, the process will go in reverse and we coalesce these pages back up, and then therefore we keep as many pages at higher order as we can because they're in scarce supply. So this works well for us. And in order to represent this physical memory, we need metadata. So similar to VMA, this is metadata for virtual memory. We have metadata for physical memory. And this is what we term a folio. So every page that's dished out by the physical allocator is kind of a raw thing. But when we are able to map stuff into userland, then we use this representation. And it can be of any valid order. And it's physically contiguous, virtually contiguous, and mappable to userland. It's describing physical memory of that nature. So whenever we're talking about physical memory in the kernel, we're normally talking in terms of, when it relates to userland, we talk in terms of folios. So one bone of contention here, or very confusing thing a rod we've made for our own back really in memory management, is the sense of what's anonymous and what's file backed. So I'm kind of briefly go over the concept, but you may think, so it turns out actually, just to preface it, you can map files into memory via mmap. That's very useful, and especially when you're executing, bringing libraries in, or you're executing a file, or executing a program. But then what's anonymous and what's file back? The most obvious explanation is anonymous memory is when you don't back it with a file, but that's not true. From the kernel's perspective, VMAs are anonymous if they don't map a file, but folios are anonymous if they don't live in the page cache, essentially. This is already going to get confusing, so maybe that's half the point here, to kind of point out that there's a lot of complexity here. But the page cache is as it sounds, it's a cache where we store folios that relate to for files. So it's much faster to read from memory than it is from disk, and therefore we cache everything in memory, and then it gives us a place where if we need to write stuff back to disk, we have a place to store that information in the meantime. So yeah, there's probably a better distinction from the point of view of folios is whether something is swap backed or file backed. So the reason I'm kind of going into the complexities here is there's actually a really obvious case where there's, or a very commonly used case, where these lines blur, which is shmem, which is essentially tempfs, right? So that's file backed, both in terms of the VMA and folio, and exists in the page cache, but it's swap backed. So if that memory ever gets freed, it goes to the swap rather than to a file, and this is what the swap backed to file backed means. And we have created a very confusing situation with this terminology. Typically, when we're talking about anonymous or file backed, we are talking about it at the folio level, but taking into account that sometimes we need to consider swap backed versus file backed. And another example of where we can cause even more confusion is you can memory map a file, map private, which makes the folios and the VMA file backed until you write to it, and then we copy it, and then you have anonymous and file backed folios in the same VMA. Okay, so nice and simple. I'm going to very briefly talk about this, the reverse mapping. So when we have a VMA, we know which process it belongs to, we know the range it describes, and therefore we can go and traverse the page tables and manipulate page tables as we need. Often we're dealing at the folio level. For instance, when you're dealing with files in the page cache, everything's in terms of folios. So you need to truncate a page. You should unmap it from everywhere it's mapped, or you're going to have a problem. So going from the VMA down to the page tables is easy, but you need to be able to go the other way, essentially, and you need to be able to do it efficiently. This is what the reverse mapping is. And this is where anonymous versus file-backed comes into play. And this is very much whether the folio is anonymous or file-backed determines this. There are two different kinds of reverse mappings. One is a lot more complicated than the other. The anonymous one's a lot more complicated. We'll go into why in a little bit. But yeah, just to make you aware that this exists, and there's this complexity here. So now we've gone through all of that, kind of going very quickly through a lot of memory management principles. Let's try again. Application, malloc, glibc, some kind of internal implementation details, break, mmap, get a VMA, could be in the middle, could be merged, later a page fault, allocate page levels as necessary, allocate physical memory and map it all in. Well, not quite, because the memory might not stick around, and don't worry, I'm not going to go through all of these. The point of this slide is to indicate there are many different ways in which this can happen. So we'll go over some of the more important ones, and probably the most important one is reclaim. So reclaim is where the kernel needs to free up memory under memory pressure. Memory pressure occurs when you're basically running low on memory, and we designate whether this is the case or not through watermarks. So when the memory reaches a low watermark, and it's kind of heuristically determined, and various aspects come into play as to what these are, but when you reach the low watermark, we start what's called indirect reclaim, so a background process, case swap D, tries to free up memory. And when we reach minimum watermark, and things are very serious, we will start to block mapping calls until memory reaches the appropriate level, and if it goes further than that, we have the OOM killer. So I'm going to talk about the classical reclaim algorithm here. There is multi-generational LRU now, but don't really have time for that. So one of the key means by which we can do this and implement what we try to do here, which is a least recently used LRU algorithm, or actually an approximation to one, because that's the only efficient thing we could do, really. We make use of these bits that I referred to earlier, the page table flags, and one of these is called the access flag. And if it's set, it means that the CPU will set it, right, whenever that page is accessed, and this is in the leaf page table level. And the really powerful thing here is the kernel can clear that. And so you can then see this page has been accessed since I last checked. So the prod algorithm, and there's two sets of these for file backed and swap backed, which is an important distinction because tempfs lives in the swap backed one. So generally, it's kind of fairly simple. We have two linked lists, one called the inactive LRU, one called the active LRU. And at the front, we work from the front, and we look at the folio right in the front of it, and we say, what's the access bit? And if it's cleared, then we initiate reclaim. And it's under memory pressure when we start processing these, right? If it's been set, we want to really be sure that it's being accessed, so we set another flag on it, the reference flag, and put it to the back. We clear the access bit, put it to the back of the list, see it go through again, and if it's set again, then we know you really are using it, and so then we put it on the active LRU, which is a list where we try and keep all the folios that you really are using, so to keep them away from reclaim. And for the active LRU, it's a similar kind of thing, but simpler. If the access bit is set, then we put it to the back. If it's clear, then we put it to the back of the inactive LRU. And every userland map folio is on one of these lists. There are some exceptions, we won't go into that, but generally speaking, and they just get put to the back of the inactive LRU by default. And how does the reclaim work? If the memory is file backed and clean, which means that there's no data to write back to disk, then we can simply clear the entry and free up the folio because we know we can read it back from disk. If it's anonymous, it's more complicated because we need to write out to swap. Either way, the key point here is you thought you had the memory mapped, you thought that it was faulted in, and now it's not there anymore because that memory will fault now. So swap, I'll briefly go over this. We need to have something similar a bit to the page cache for anonymous memory when we go ahead and put things into the swap. This is called the swap cache. And there's a bit of a timing thing that happens here because writing back to disk takes some time. It's an asynchronous operation. So what we do is when something's swapped out, we put the folio into the swap cache and we replace the PT entry with what's called a swap entry. And here's the power of virtual memory. We're able to put enough information in that entry to locate that memory in the swap, and we can set a certain bit to tell the CPU to fault on it. And once it's in the swap cache, we can kick off the asynchronous write back, and when that's complete, we can free the folio from the swap cache, but we leave the swap entry there so you know where to look it up if somebody should fault it in again. And swapping in is kind of the reverse of that. Firstly, we check to see if it's in the swap cache, if somebody's immediately tried to fault it back in, and we just put it out. And if not, we start an asynchronous read and we block that until the operation is complete. And when every swap entry is gone, we can put it out the swap cache as well. So this, we're going to be briefly touching on. This is where anonymous memory is complicated, or why it's complicated, which is really forking. So it's a lot more efficient when copying memory from a parent to a child to just copy the page tables rather than the data. And when you do that, you can't just keep everything read-write for anonymous memory because it's not shared and you know, that's not what you want. So what you do is you mark it read-only in both the parent and the child, and that then gains copy-on-write semantics, which now means that that folio is mapped in more than one place, even though it's anonymous. And there's some very complicated bookkeeping that's required, and it goes pretty deep, that. And then when somebody tries to write to it, and here again, the memory you thought you had, now it's read-only. So when you write to it, we'll copy it into a new folio, unless that is the only place it's mapped, in which case we can just make it read-write. So, and yet another way, I'm kind of going through the main ways this memory can be moved around, is compaction and migration. So we do try to avoid fragmentation as much as possible, and this comes into play when we need a higher order allocation. And one way we do that is we keep kernel allocations away from userland, because the migration part of this is that userland mappings, because we control the page tables, we control the faulting, we can move them around, we can put a different physical folio in place. But with kernel mappings, we can't do that currently. And in order to reduce fragmentation between the two, we keep them apart at a granularity called a page block, which is typically order 9. And then that way you avoid kernel allocations causing fragmentation for userland ones. But that's, you know, this is not always enough, and so there's something called compaction that can occur, where you determine that there simply isn't the ability to obtain a higher order allocation, or the fragmentation is high enough that you want to do something about it. So typically we kind of take a hammer to it and we pull all the folios out of a page cache and put them into a more suitable location, and then we can allocate from that page block. So here your memory might be moved. And the way that works is we isolate each folio from the LIUs, so they can't be reclaimed. We then use another special kind of entry, here again, virtual memory being highly useful, which encodes the information we need. It's called a migration entry, and faults when you try and access it. Find a suitable location for the previously mapped memory, copy it over, and then once that's complete per folio, then we replace the page table entries and get rid of the migration entry. And the migration entry, if you try and access it, will either block for the operation to complete, or it can also fail. So again, we see that things are very fluid. So we come to take 4 of where does my memory come from. We have an application, we mal it, go to glibc, some kind of magical internal implementation details, break an mmap, put a VMA in place that could be merged. Later there's a page fault. We allocate the page tables as necessary, allocate the physical memory, map it in, then maybe we page fault again. And this is where a lot of the complexity lies, right? And then the kernel fixes it up. And in broad terms, this is how it is. So what are the conclusions here? We make allocating memory easy from userland. There's a lot of complexity underneath. Managing resources and abstracting complexity is the kernel's job. Memory is a lot more fluid than you might think. It moves around. You can flicker in and out of existence, but when you need it, it's there, mostly. And virtual memory is very powerful. So, yeah, that's about it. Any questions?
Hi, thank you for the talk. So I have two questions, both of them may be based on incorrect assumptions. So the first one is that when you perform the RMAP walk, and in the case of copy and write pages where two different address spaces may share the same underlying page, how do you walk from the page to the, how do you decide what the intended MM struct is when you do the reverse map walk?
So how do we determine which VMA to go to on the RMAP walk?
Not the VMA, but one step above the address
page
space, the MM struct. So since two different MM structs can basically map the same page or hold the same page. Mm-hmm. So when you do the RMAP walk, do you end at the VMA struct or do you go above that into the MM struct as well?
Well, you traverse through the page tables. Each MM struct will keep track of the PGD related to the process, so then you can. So yeah, you go all the way up. In fact, there's kind of a little bit more to it. It's like I guess I could go back to the slide. There we go. There's an interval. This thing above the mapping object is an interval tree. And so there could be multiple VMAs, and these have certain ranges. So you only traverse the ones that could potentially contain the range. And we actually we go up to the VMA and then back down through the page tables, typically. And then we go to the folio and we check to see if that folio is the one we wanted.
Okay. So you walk back down to the
folio.
So
you got to go up and then down again.
All right.
It's expensive.
And my second question, you didn't discuss it in the presentation, but it's with regards to memory accounting. From what I understand, when you charge memory, you charge whenever you allocate a new folio. So once the memory is swapped out, is it still charged to the process or not?
I'm not so sure, Matthew. I'm not so familiar with the charging side of it.
It depends. RSS isn't charged?
Yeah.
So RSS wouldn't be charged because that's resident set size. It's now swapped out. It's not resident anymore. But I forgot the name of the other counter, VSS, the virtual set size, that's still charged because that is your virtual working set size. There's a man page for this.
Yeah, but MemCGs don't care about VSS, but I think there's a separate swap accounting, so you can have limit on that.
And does that show up in the feature memory accounting side?
I think it's showed in separate counters. If I remember correctly, MemCG V1 had some. Oh, you can answer that better, right?
I think MemCG V1 has one shared counter which accounts for both memory and swap altogether, and then there is a separate counter for just memory. C group V2 has two separate counters for memory and swap. So like whenever you swap in a page, like a swap counter will be decremented and memory C group counter will be incremented.
So I know that folios are like the new pages, and that we're supposed to use them instead of pages, but what's the actual difference?
Matthew is best to answer this.
Okay, so I covered this 2 years ago, but I'm going to go through it here in this room, but I'll go through it again for those who weren't here. So we started out with the Ottawa interpretation of the meaning of struct folio, and the names are recent, but the Ottawa interpretation is that struct folio is simply another name for the first page of a potentially multi-page allocation. So it is simply a duplicate of everything, but you're guaranteeing it's not a tail page. It might be a single page, it might be the head page of a multi-page allocation, but it is not a tail page. And that is a useful improvement because that lets us not call compound head all the time. It lets us be absolutely clear that we are definitely talking about an entire allocation and not specifically about the precise page that is being pointed to. Because we had functions that were making all kinds of different assumptions, and from the point of view of anyone trying to learn it, like me, I couldn't tell what any given function was expecting to see. So that was a huge improvement in code clarity. Now we're moving towards the second interpretation, what we're calling the New York interpretation, because that's where Johannes lives. I live in Ottawa. So in the New York interpretation, we're actually separating the two data structures. We're separating struct page from struct folio. And that lets us shrink struct page. And that's an advantage for memory consumption. When you boot a kernel today, it takes about 1.6% of your memory and reserves it for this thing called memmap, which is basically a giant array of all the struct pages in the system. It's more complicated than that, but you don't care. So people at cloud computing companies tend to use metaphors involving setting giant piles of money alight in the parking lot every month. It's very dramatic and fun, but the idea is that 1.6% of memory could perhaps be better used. So I have a plan to get struct page down to about 8 bytes. I'm not going to get there this year. This year I'm hoping to get down to 32 bytes for struct page. And then the flip side of that is that struct folio remains at least as large as it ever was and maybe gets slightly larger, but you're only paying the cost of allocating the struct page per allocation, whereas the cost of struct page is paid for, well, every page at all times. And so when you have, 4 pages allocated to give yourself a 16 kilobyte allocation, most of the information in the tail pages is either not there or just duplicative of what's in the first one. So we don't need, 64, 120, we don't need that 256 bytes of memory. We can shrink that 256 bytes of memory down to 432 kilobytes and then perhaps a 96 byte allocation as well. And that will improve over the coming years. Downside, it is an extra dereference to get from struct page to struct folio. So if you're trying to do some, we were talking about this with Slab the other day. So if you're looking to go from a virtual address to the struct slab, you have to first go and look up the struct page that you're referring to, and then go to the slab. So it's 2 pointers being chased rather than one. So we may see a performance degradation in some workloads. TBD whether the trade-offs are acceptable to the wider Linux community. Sorry for taking so much of your time. He did ask.
Hello. How much of what you presented is hardware assisted or architecture specific?
Well, the page table stuff is all hardware. Yeah, I mean, that's the virtual memory implementation is entirely based on the hardware, and things like higher order folios, to make use of them, you may then be using hardware features like THP or MTHP if you use lower order on architectures that support that. And really, we have to be enabled by hardware to be able to implement the virtual memory features that we do. So, for instance, our access bit and numerous other things like being able to set things read-write and so on. So fundamentally, the virtual memory bit, I'd say, is the key bit, yeah.
Oh, you're so modern, Lorenzo. This is common on all current CPUs, right? But PowerPC used to use hashed page tables. And there have been other crazier schemes dreamt up in hardware that I'm not going to go into because too much time already. But yeah, this is just what modern hardware does. Yes. Other people have done other things in the past. This is perhaps the best performing.
Cool. Thank you very much.